Okay, okay, this is working too. Yes, this is working. We'll see how that works. All right, so let me come back over here. So I have already uploaded this set of notes. I'm going to use them today as well. And this is our last chapter on hydraulic fractures. And let me go down. And we're going to be going back and forward through these notes. Okay? But I just wanted to let you know that the slides are already here, but I still have to write up what they mean. But I'll try to have that done by next week, if possible. I also have to grade exams and do a few more things, so it might take a little bit more time. All right, so we're going to start our talk of hydraulic fractures by extending what we learned from the wellbore environment. So already you know very well that you don't want a pressure in the wellbore which is too high. Well, first of all, you don't want a pressure in the wellbore which is too low, because what is going to happen if your pressure is too low in the wellbore? Say again? Breakouts, right? Shear failure. So that's not going to be good. That may cause wellbore instability problems, and in order to that, you have to increase the pressure. But if you increase the pressure too much, then what's the problem with that? Tensile fractures, right? So let's try to see what happens when you pressurize the wellbore too much, and how we link this to the leak-off test. We talked about the leak-off test before, but we didn't give a lot of details about the signature of that leak-off test. So imagine that you're drilling a vertical wellbore where you have far field stresses, SH min, SH max, and SV, and we're going to assume that we are in a normal faulting regime. So this is going to be SV, SH min. I'm just drawing half of the wellbore, and I know that SV is higher than SH max, it's higher than SH min. My hand is a little bit cold, I can't write, but this is what we have seen so far. I'm going to do one more simplification here. I'm going to say that SH max is going to be equal to SH min, and I'm just going to call it SH, just to make things a little bit simpler. Okay? So what would be the equation of the breakdown pressure? Do you remember the equation of breakdown pressure? PB is, for sure, has to be higher than the pore pressure, and then it's
3 times sigma
H min plus minus sigma H max, right? And minus sigma H max plus the tensile strength. All right, so let's say now that if these two are the same, because the total stress are the same, then PB is going to be PP plus, this is going to be 3 minus 1, it's just going to be 2, sigma H plus TS. So this is the equation that we will have if we have an isotropic stress field perpendicular to the wellbore. That will be our equation for the breakdown pressure and for having a tensile fracture in the wellbore. All right, so hopefully from now before it might not have been quite clear because we didn't get up to this point, but let's see what is called breakdown pressure and what is the comparison of that with the minimum principal stress and the pore pressure. And for that, I'm going to assume something now a little bit more realistic. It's going to be a problem in which we're doing a leak-off test. If you remember, a leak-off test, it's a test done by drillers. So they get to a point in which they stop drilling. You either case the wellbore or you might want to put some packers and pressurize the wellbore. But let's assume in this case we get with a casing here and you run the cement and you cement this wellbore, and after you do that you put a plug over here and you pressurize this area of the wellbore. Okay, so we're looking at the cross section of the wellbore that we have plugged and in which we can inject more drilling mud. And we're drilling, okay? So we're drilling, so this is drilling mud. Okay. The pressure inside the drilling mud is going to be PW. And now this pressure PW is going to be a function of the density of the mud, as we have seen before. Is going to be a function of the true vertical depth. But now we're going to start injecting, and this is a closed volume. So if you start injecting in a closed volume, you will expect what's going to happen with this pressure. It might increase, right? If you're injecting fluid in a closed volume, the pressure very likely will increase. All right, so let's imagine that we run this leak-off test as a function of time, and at the beginning I do not inject anything. This is going to be the rate of injection. I do not inject anything, and PW is just the hydrostatic pressure of because of the column of drilling mud. At some point I'm going to start injecting at the constant rate, then I'm going to stop, and I'm going to inject again, and I'm going to stop. My objective is going to be to understand what is going to be the signature of the pressure in the wellbore. So if you were to measure this pressure, which is often done, what would be the signature of that? All right. So in order to do that, we're going to make a plot here of PW as a function of time too, and I'm going to assume that I start. This is the pore pressure, so you see that value is this value over here. We're going to start with the pressure in the wellbore, which is slightly higher than the pore pressure, and I'm going to assume at that point there are no breakouts. So that's the pore pressure, and I'm going to say that if I don't inject any drilling mud, then I shouldn't have any additional pressure, right? So the pressure in the wellbore is just going to be that. That's a starting pressure in the wellbore. I'm not injecting anything, okay? Injection rate is equal to 0. All right. So now I'm going to start injecting at this point. What's going to happen with the pressure in the wellbore if this is a closed volume? Do you agree with me that it's going to start to increase?
Yeah.
right? It has some compressibility. This wellbore, it expands a little bit, but not a lot. So it's going to start increasing. But the question is how much. So I'm just going to draw a line over here that goes kind of forever, but we're going to challenge this assumption. How much can PW go in this wellbore? Can it go forever high? No, right? So what is going to be the maximum value?
Like the wellbore cracks.
Okay, and how much is that?
Breakout pressure.
No. Breakout it was for shear, right?
Breakdown.
The breakdown, this one, right? So let's look at this equation. This is actually telling us how much the pressure can go at the moment we have breakdown. Look, we're already at the pore pressure value. We're above that. What this equation is telling me is that I can go as high as 1 horizontal effective stress higher, 2 horizontal effective stresses higher, and the tensile strength. So this is as far as you can go in the pressure in the wellbore. You cannot go higher than that, because at that point you're going to start causing a tensile fracture, and that tensile fracture is going to be filled with drilling mud and it's going to propagate. So actually now this curve is going to reach a peak at this point, and now the question is, what if it's not going higher? Is this going to stay at this value, or is going to be higher than that? It cannot go. We already saw that. This as much as it's going to go, but now it's going to go down. It's going to stay there. What do you think? I keep on pumping. The injection rate is constant. Any thoughts?
Can you repeat the question?
Yes, I'd like to know what happens with pressure here, because we said that we increase pressure as we are pumping. Now we're starting a fracture in the wellbore. I want to know what's going to happen with the pressure. If it's going to continue the same, or if it's going to decrease with time after we initiate the fracture. Okay, so okay, let's, in order to help a little bit, let's see what's going on with the wellbore at different times. So before I have any fracture here, the wellbore, it looks fine. It looks circular, no fractures, and this PW. When I get to this point over here, I start to have a tensile fracture. It's a tiny tensile fracture, but I already start to have that. My question is, what's going to happen after this?
It'll decrease
Why it will decrease?
because there's less pressure with the fracture.
Yes.
I think it depends on the fracture.
It depends on the fracture propagation velocity. So there can be two scenarios, extreme scenarios over here. If the fracture propagates very quickly, quicker than the mud that you can inject, the pressure is going to go down. If your fracture is propagating at the same velocity at which you're injecting drilling mud, the pressure is going to stay more or less the same. But usually here at the beginning of this fracture propagation process, these fractures are very quick. We're going to run an experiment on Thursday where we're going to do one of these fracture propagation tests, and you'll see you won't even see the fracture propagating. Probably if you do a slow motion video, you'll get to see the fracture propagate, but otherwise you will not. An in-class experiment, don't worry. You don't have to go to the lab. So if the fracture propagation velocity is very high, you will see that this pressure is going to start to decrease. And that's because, as I explained before, the fracture propagation velocity is so high that at the rate at which you are injecting drilling mud, you cannot keep up with that new fracture volume. Yes?
Is this phenomena similar to the one that we did in the earlier labs where we were applying force, and sometimes it would just like, if we look at the force, it would show that like it becomes constant, and sometimes it would just like instantly decrease. Like
Yes, it's similar to that, because sometimes some of those fractures and shear fractures too, they propagate very quickly. But now it's also similar in the sense that in the lab you were applying a constant rate loading, and here we're applying a constant rate injection, which is also some other type of loading. Okay, now the question is how low is this going to go? You see, I'm continuing here with the injection constantly. So what do you think about that? How low can that pressure go? Will it go? Let's try to see the extreme cases. Will it go lower than pore pressure? Not very likely, right? What will be the next lower bound for that pressure to go? I'm propagating a fracture. It's propagating as we inject fluid. What is PP plus sigma H? It's SH mean, right? Or as we call it over here in the equation, just SH, but SH mean was equal to SH max. And notice that here this one is SH mean or just SH, the horizontal stress. So if the fracture is propagating, as we said before, it cannot go lower than the minimum principal stress. And that's the one thing, if you're going to remember something about this class, that I want you to remember, okay? That in order to propagate hydraulic fracture, your pressure has to be equal, most times higher than the minimum principal stress. So definitely, if I'm propagating this fracture, the pressure is not going to go lower than the minimum principal stress. And in fact, in order to propagate this fracture, you are, and as we're going to see later on, you're doing quite a bit of work. Which work? You need to flow fluids through the fracture. Those are some viscous losses already. You have to break the rock here at the tip of the fracture. There's going to be tension, and breaking that rock also takes work, takes energy, and all of that energy is going to come from the pressure in the fluid. And because of that, the pressure at which this signature is going to get to more or less a constant value is going to be higher than the minimum principal stress. How much higher? It depends on many factors. It depends if you are doing your fracturing with drilling mud, with a slick water fracturing fluid, or with something else. But the difference between that fracture propagation pressure and the minimum principal stress is something which is called net pressure. And that's something also very important to remember. It's the additional pressure that you need in order to propagate fractures. If you're at the bare minimum of SH mean, there might be some likelihood of propagation of fracture, but it's not going to be very fast, very likely, and it may not propagate that much. In order to propagate a fracture constantly, you need a higher pressure. And that, how much higher, is given by this value P net. Okay, so notice that now I have made this propagation pressure to reach more or less a constant amount, and now it's not varying anymore. This is an assumption I'm making. As we're going to see later on, sometimes this pressure goes up, sometimes it goes down, but if we'll assume for the moment that that's more or less a constant pressure. And at that point, we're also assuming that the drilling mud is catching up with the velocity of fracture propagation. Or actually, well, it's not really that the drilling mud is catching up with the velocity of fracture propagation, but it's more like the fracture propagation velocity is adjusting to the amount of injected drilling mud. So as you keep on injecting drilling mud, now the fracture opens as a response of that additional amount of drilling mud injected, and they both happen more or less at the same time. The same injected volume is the same volume that now the fracture has opened, so it reaches a more or less constant pressure. At this point, we already have a propagating fracture, okay? And it's not just to one side, it's going to open to the two sides. So this is drilling mud flowing, and it's also, we may have some leak off through the fracture. Remember that here we're doing a test on an uncased section of the hull. Now we have a very large fracture. It's much bigger than this tiny case at the breakdown pressure. Okay, so very important to remember. Pressure increases because it's a closed volume. How fast it increases depends on the compressibility of the drilling mud and also the formation compressibility. The peak value is the breakdown pressure. That it's given by the equation that we saw before. And after that, it goes down because the fracture propagation velocity at the beginning is much higher than the injection rate, and then those both more or less get to the same values, and the pressure gets stable. All right? So far, so good? Any question about this before we continue with the test? No? Okay, before we continue with the test, let me tell you something else. So why would you do this kind of test? Because you want to know how high you can go in pressure inside the wellbore in order to extend your mud window. Sometimes we use a conservative value of the minimum principal stress as a conservative value, but if you know your wellbore well, and if you know your rock, and you have a lot of certainty about that additional tensile strength and those additional horizontal stresses effect, you can go a little bit higher. Okay. This is called an extended leak-off test because it goes into a large fracture propagation. Some people do what is called a short leak-off test. I don't remember the exact name, but they stop when they see that at this point they lose the linearity of this curve. They will stop the test at this point somewhere over here, and they will just come down in order to avoid doing this large hydraulic fracture in the wellbore. Okay, so up to this point we're there, and we're injecting at a constant rate. Now we're going to stop injecting at this point. What's going to happen with the pressure response? It's going to drop, right? If you stop injecting, the pressure is going to go down. Why does it go down? Why would it go down?
There's less force from the top because there's liquid pushing the other liquid more than it's gravitational force.
No. I think I see your point, but if in many of these cases, we may assume that there is no return of the fluid. That everything you inject stays there.
Yeah, so like if it's being injected, that means that there is
Yeah.
constantly more fluid pushing it in, but once it stops, okay.
No, but at this point, there is no more mud getting into here. The pressure goes down because there is a leak off. Some of the water in the drilling mud is getting into the formation. Your pressure is much higher than the pore pressure, so some of the fluid will filtrate through the rock and will get into the formation, and it will be like a leaky reservoir. So if it's a leaky reservoir and you have leaks, your pressure is going to go down. How much is that pressure going to go down? That's the next question. So we know it's going to go down. What do you think? What is going to be the absolute minimum value for this pressure to go down?
Or pressure?
The pore pressure, right? It wouldn't go lower than the pore pressure because the pore pressure is this value over here. Why would it go lower? If you were to live for an infinite amount long time, it would just go to the pore pressure. It would equilibrate with the pore pressure. But well, let's assume that this is a very permeable formation. As soon as you stop injecting, your pressure is going to go down very quickly, and then it's going to start to reduce with time, and it may approach the pore pressure. Now remember, you're not injecting anymore, okay? There is no fracture propagating. Actually, if there was a fracture in this case, probably now the fracture is closing, and it is closing. And actually, let me improve this plot. And if you let the pressure go down a lot, what was open before now is going to be closed. Okay, can you see that? So the fracture at the beginning is full of mud, drilling mud inside, and you stop the pressure, and the pressure starts to go down, so the fracture is going to start to close, and the drilling mud is going to start to get into the rock, and at some point it's going to close. The point at which it closes, that's what is called the fracture closure pressure. And that fracture closure pressure is more or less equal to the minimum principal stress. So if you find the point at which your fracture closes, at this point you just have leak off from the wellbore, you will be able to tell and to predict what is the minimum principal stress at that case. Before that, there is something which is called the instantaneous shut-in pressure. And before that, I forgot to write over here, this value is called the fracture propagation pressure, and this value, as we saw before, it's called the breakdown pressure. And this value, let me exaggerate this a little bit more. So we're going to have some linearity, and at some point this is going to kink. The point at which it kinks a little bit, that's called the leak off point. And let's see if I'm forgetting anything. No, we have the P net, fracture closure pressure, instantaneous shut-in pressure. No, we have all the pressures that we need. So notice that at this point, the fracture closure pressure, now you have leak off just from the wellbore. Okay, this is going to be very important because we're going to come back to this. And any decrease in pressure is just going to depend from filtrate water coming from the wellbore rather than from the fracture. What was in the fracture is already into the rock. Okay, so let's see the injection schedule. Yes, Michael.
So the instantaneous shut-in pressure, is that where it starts to not just drop straight down pressure after you shut in the wall?
Yes, it's after you will turn off the pumps, the pressure will go down instantaneously, and when it starts to pick up a variation, that's going to be the instantaneous
Okay, and how
shut-in
do you
pressure.
determine the fracture closure pressure?
That's what we're going to see later.
Okay.
And it's a very basic concept, and we also are going to do that in the homework. Okay, but it's related to the difference going from here to there. But I'm going to explain that in detail in right after this. Let me finish with this leak of test. So now you're going to inject again drilling mud. How far is the pressure going to go? Let me just draw a line here, but definitely it's not going to go higher than the previous PV, right? Because we said that it wouldn't go higher like this. But look, now you're repressurizing this fracture. So what is the difference with the case before? There is a difference. So what is the difference? Tell me how much higher the pressure can go. The answer is in that equation. Say again?
Not as high as before.
But how much? Tell me exactly how much is going to go.
Oh, it will go PP plus 2 sigma H,
And why?
because it's already fractured and there's no tensile strength.
It's already fractured, right? There's no tensile strength. So you cannot count with the tensile strength bump anymore. It's just going to go as high as this. And that value, according to this plot, is somewhere over there. And it will go up, and notice that it's going to reach a peak. At that point, the fracture is going to open again. It's going to start propagating, and assuming that we reach into this extended fracture propagation, then it's going to drop again, and it's going to reach again that same fracture propagation pressure. And after you start injecting, it's going to drop again. So this will be the wellbore response for the first leak of test, and then the second leak of test with the formation already fractured. So let me draw again this. The fracture now is propagating, and is actually now longer than before. So in the leak of test, you are doing a hydraulic fracture, but the objective is actually to prevent that hydraulic fracture when you're drilling. So you just do it once under controlled conditions, but you don't want to do it under uncontrolled conditions with a huge open section of the wellbore. So just do it once. You test what is this maximum value to which you can go, so you can extend the mud window, and that's it. You do not want a hydraulic fracture in this case. Just do it once. but then you do not want that. But it's very important to know what is that maximum pressure, because you get information about what will be the fracture gradient. And also from these tests, now you can see that we can determine what is the minimum principal stress. Most times we do not know what is the minimum principal stress, and this is one of the best ways of measuring that. We use these equations of tectonic strains, of limit equilibrium, for trying to estimate what is the horizontal stress, but most times we do not know that, and you need to measure that. And this is one way of measuring that minimum principal stress. So let's see then more into detail what's going to happen in this section at the fracture closure pressure, and how you're going to be able to determine that minimum principal stress. So, but remember, the main takeaways from this leak of test is: one, the breakdown pressure, which is going to tell you what is your fracture gradient, absolute maximum fracture gradient, and two, that you can measure the minimum principal stress. Why you want the minimum principal stress? Because knowing that value, you know that you need that to calculate breakouts, to estimate also tensile fractures, and many other things that are useful for geomechanics. So let's make a zoom now into this region. At that point, if you measure the pressure in the wellbore, you will see that there are going to be two distinct regimes of the decay of pressure. Your pressure signature, in ideal cases, is going, sometimes a little bit more complicated, it's going to look more or less like this. When you plot pressure as a function of the square root of time. So you get this data of pressure as a function of time, make this time equal to 0, and then start measuring from that square root of time, and you will see that you can make this plot. So what's going on over here? Why do we have a change? The change is due to the fact that before this point, you're going to have a fracture which is open, and it leaks off from the wellbore, but also from the fracture. Because your pressure, yes?
I just had a question why we have square root of time on the x-axis instead of just time.
Because that's going to help you realize when you have radial fluid flow and when you have linear fluid flow. It's it's just to see that difference. When you plot pressure as a function of time versus square root of time for a system like this, is going to line up in a line, but when it's radial flow, it's not going to line up in a line. It's going to be a curve. So here the fracture is open, okay? And when the fracture is open, this is similar to having a linear source of pressure. So this would be equivalent to say, if I have a far field like this, I have a source which is a line. Pressure is dissipating from this line. However, when your fracture closes and there is no more pressure, well, there is a pressure which is equivalent to the far field pressure, in the fracture, but when the pressure which is significantly higher than the pore pressure is going to be mostly in the wellbore, and at that point this is going to be equivalent to radial fluid flow. And those two cases are quite different, and you may expect that if you have a long line in which your pressure is or your fluid is being injected from a constant volume, that's going to decrease very quickly because you have more surface area. As when you get to this point, the fracture is closed, now you just have small wellbore, the tiny wellbore from which pressure is decreasing just from here and with radial fluid flow. And as you can see in the signature here and this schematic, you will expect your pressure to go down more slowly because now you're not injecting from a linear source, but you're just injecting from kind of a point source. This point that separates the fracture from being open or from being closed, and the same to have like a linear source or a point source, is what is going to allow you to measure the value over here is going to be your fracture closure pressure.
Professor?
Yes.
So when we have an open fracture, aren't we going to also have more leak-off?
Here?
No, in the open fracture.
Yes.
So,
So that's why your pressure goes down more quickly.
okay.
And when it closes, now you do not have as much of a surface area contributing to that leak off, but you have much less, and it goes down more slowly. Oh, okay. So let me see. What I'm forgetting over here. Let me add to this plot in this case the area of leak off is going to be the area of the wellbore in contact with the formation plus 2 times the area of a fractured wing, right? And in this case the area of leak off is just going to be the wellbore. But is this difference going from this type of fluid flow type to this one that makes the difference in the signature of the pressure. It goes down very quickly at the beginning. When it closes, it goes down much more slowly because there is less area for leak off. All right, so let's see some real cases that I have over here that probably will help us see this a little bit better. I'll come back to these dikes later on. So this is the same thing that we drew before. Some acronyms over here. You don't have to remember the acronyms, but as long as you remember the concepts, that is going to be fine. And this is an example of a, let me put this full screen. This is an example of a real test. So some people also may call it a little bit differently. Here they call it, instead of leak-off point, fracture initiation pressure, but the signature is more or less the same. You have a linear response, then you have a kink. The breakdown pressure, some other people call it the point of uncontrolled fracture propagation. Then you go into this regime in which the pressure is more or less constant. We're going to see later on that sometimes it decreases, sometimes it may increase. It depends on the fracture geometry. And when you stop injecting, you have the shutting pressure, instantaneous shutting pressure, and the fracture closure pressure. So And once you have this signature of pressure as a function of time, you can put that data, and actually, this looks very nicely, in terms of pressure as a function of the square root of the time after the shut-in pressure. So you see this delta T, and at the point in which there is a departure from linearity, that's going to be your fracture closure pressure, that some people also call it FCP. Okay, so I may have one more figure. This is real data again for a extended leak-off test and how the pressure goes down, and that's what drillers do. Okay, let's talk about now how we can use this also for completions. So drillers, they are interested about fracture gradient. They want to measure what is minimum principal stress to improve their wellbore design. In completions, you are also interested about fracture propagation, but this time you want to propagate fractures, and you want to propagate them at the lowest pressure possible and create the maximum surface area possible. And for completion, you also want to measure what is that pressure for propagating fractures. But now the test is going to be a little bit different. And this test is usually called, it goes by the acronym of DFIT, and that stands for Diagnostics or Diagnostics Fracture Initiation. Basically, what we want to measure now is the pressure at which you will propagate a fracture, right? But now notice that this is different. It's different than what we did before. Why is it different? First of all, because it's for completion purposes. So the first one was for drilling. This one is for completion. Because it is for completions, many times, instead of doing it in an uncased wellbore section of the wellbore, you do it in a cased section of the wellbore. And let's imagine that we have a horizontal wellbore that it's plugged and it's cased. In order to get to the rock, you need to make a perforation, right? And in order to make the perforation, then you have to have perforation guns. And now this test you're going to run in through those perforations. Sometimes you can also do it before casing the well with a small pad that goes on the wellbore and isolates a section of the wellbore, and you do this test over here. But let's go to the case in which you already have a perforation. So it's different than before, right? So now this is for completion. What kind of fluid are you going to use if you're doing this kind of test? Are you going to use drilling mud? No, right? So probably you're going to do this with whatever fracturing fluid you're using. Probably you can test several types of fracturing fluids in this case, and many times you're going to do this through perforations, and you're going to do it before a large hydraulic fracture treatment, and usually, one more thing, this is done in low permeability reservoirs. Why? Because if they have very high permeability, most times you don't need to do a fracture. So mostly you need fractures whenever you have low it's very similar to the case before. We're not going to go into details about how you measure fracture closure in this case. Some people claim that out of this pressure signature, let's say now this is not the wellbore pressure, but it's the pressure of the fracturing fluid. You want to see something very similar, pressure that goes within a constant injection rate, goes up, then goes down, reaches a more or less constant value, and you have instantaneous shutting pressure and a decreasing pressure with time, very similar to what we saw in the leak-off test. But the analysis is a little bit different. In low permeability formations, it's the same concepts apply, but it's a little bit different. And some people use what is called a G function, and it's basically a way of converting the pressure data into something that you can associate with different types of flow regimes and with fracture propagation modes. And from here, same as before, you get your minimum principal stress, but also you can get what is the permeability of your formation. Many times you can call that an effective permeability because there are going to be some fractures in that formation. But it is exactly the same. It's the same concept. It's just a little bit of a different analysis. And I have an example over here. So this is a DFIT test. Something very small, something very important I forgot to say. For the DFIT test, usually you test with very small volumes, and because you don't want to do a high hydraulic fracture at the beginning. But as you can see over here, the injection volume is less than 10 barrels, and the injection rate is usually also small because you're injecting into a very tight formation, so you need very small injection rates in order to elevate the pressure quite a bit. So this is what we were discussing before, but this is this G function time. You see, you inject at the constant rate. This is real data. Inject at a constant rate, pressure goes up. At some point, the rock breaks, pressure goes down very quickly, and you reach a fracture propagation pressure, which is more or less constant. At that point, you stop the pumps, pressure goes down further. You take this data that looks like it's not changing at all, but if you magnify changes, you can get to see those variations in these G function plots, and out of here you can tell what is the minimum principal stress and what is the permeability of the reservoir. So you can get them from this type of analysis. So we're not going to see the detail of this because some of these methods they change with time. People improve them. Some companies, they claim that their method is better than others. So there's some still discussion about which is the best method to use. But remember that there is something very similar which is done for completions. And it's just a little bit more complicated. Okay, so this leads us into another kind of test. And I'm working on a homework just about field test of hydraulic fractures. And this is going to be the third one. So the first one, remember, is the leak-off test, which is done by drillers in order to avoid hydraulic fracturing and losing significant amounts of drilling mud. The second one is the DFIT test done during completion in order to predict what is the fracture propagation pressure, so you can design your pumps and you can design everything associated with it. And in this case, you do want to do hydraulic fractures. And the third case is what is called the step rate test. Yes, Mr. Ewan, you have a question? No? Okay. So the third one is the step rate test. So what is the step rate test? The step rate test is a test which allows you to measure the maximum injection pressure in cases that you are meant to be injecting fluids constantly or more or less constantly, right? So, and also because you're going to inject more or less constantly, you're injecting usually large amounts of fluid. Can you tell me examples in which you, in petroleum engineering, you want to inject large volumes of fluids?
Enhanced oil recovery.
Okay, and what do you inject in enhanced oil recovery?
CO2.
Okay.
Water.
CO2, water, polymers, surfactant. You could inject steam, right? There are many things that you could inject. What else?
What about gas lift during like regular artificial lift?
That also would apply, but usually, well, you inject large volumes there, but
It doesn't go into the reservoir, right?
no, it goes to the reservoir, but usually the rates they wouldn't be that high. But I think it will also count. There is another case in which you inject large amounts of fluid, and that was somehow problematic in the last years. Any
Wastewater disposal.
wastewater disposal. So with wastewater disposal, notice that the larger the amount that you inject, the more money you earn, right? Because you're charging your service for amount of injected water. So if you're charging your service for amount of injected water, you want to have high rates of injection, and you want to inject as much as possible. In some of these cases, CO2, polymers, even water, that costs money. So you don't want to inject a lot. You just want to inject the minimum amount so that you achieve what you want, but you don't want to inject a lot. And the same for artificial lift. You don't want to inject, say, lots of methane because that also may cost money. But in this case, you want to inject as much as possible. So in these cases now, the objective is actually to inject fluids, and usually this is going to be done in a more or less. So these are examples. This is going to be done in a more or less permeable formation. We didn't say why this one was problematic. What was the issue with wastewater disposal?
Is it causing earthquakes?
Because if your pressure goes too high, we have already seen that, what happens to the faults? You lower the effective stress, faults slip. And that slippage may cause earthquakes. And that was happening in Oklahoma. But now they are controlling that, and a large influence on that was understanding better some of these concepts. In this case, we're going to assume that we have an infinitely large reservoir. And the step rate test is going to consist, probably, I'm going to need another page. It's going to consist on injecting fluid, as the name says, in steps as a function of time, so that at the beginning, let's say this is 0, you ramp the injection and rate, and then you wait for some time, and then you ramp it again, and so on. Usually in this, you want to divide, you more or less want to estimate what is going to be the maximum injection rate. You want to make about 7 steps or 8 steps or so, but you don't want too many, you don't want too few, right? All right, so we're injecting now into a wellbore, which is it's not fractured, and I like to see what's going to happen with the wellbore pressure. Let's say that we start at some pressure more or less over here. I'm not injecting anything. What's going to happen to the pressure signature as I ramp up the injection rate? It's going to increase, right? It's going to increase, but remember that now we're working in, this is a test in a permeable formation. So let me add a schematic here to help that a little bit. Let's say that we're injecting into an uncased formation, and the fluid is getting into this formation, which is very large. So your pressure will increase, but will not increase very quickly. It's going to take some time till you reach steady state. You inject the injection rate again, then this one is going to increase till it reaches more or less a steady state point. That's the point at which you want to inject, at which you want to increase your injection rate again, and so on. But do you think this behavior is going to continue forever? If you pay attention closely or try to interpret what I drew, if I were to now plot pressure as a function of injection rate, at the beginning, let's say pressure is somewhere over here, and then it's over here, and then here, and then here. I'm assuming that in this case the increase of pressure, every time I increase injection rate, that increase of pressure is proportional to the injection rate. And that kind of makes sense, right? It kind of makes sense because if you remember the equation for fluid flow in a wellbore, any of you remember that equation by heart? That's one of the things that you should remember. I don't remember it, but you should remember it. It's Q, if I remember correctly, it's of course proportional to K divided 2 pi the height of the formation times delta P divided the natural logarithm of the radius in the far field divided the radius in the wellbore. Something like that, okay? Please check that equation. But the important thing here is that the delta P, the pressure increase between the difference between the wellbore pressure and the far field pressure is proportional to the injection rate. And this is what we see over here. So my question is now, is this linear trend going to hold forever as you keep and now you inject at some very high injection rates? Do you think that the pressure is going to still keep that linearity? Yes, no? When you raise your hand, if you say yes, and you say no, nobody? Why not, Michael? What?
I want to be linear.
Because I have this equation that tells me that it's linear.
Eventually, you're going to fracture the formation again, right?
And what's going to happen when you fracture the formation?
Yes, you're going to leak off, so you're not going to increase as much pressure
Why?
because fluids are going into the formation.
So when fractured, if you still want to use this equation, you're going to have to add skin factor. And that skin factor it physically means that, as Michael said, that now you have a fracture where the fluid is also getting into the formation through the fracture. And because you have more surface area, now the additional jumps of pressure are going to be much smaller to achieve the same increase in injection rate, because you have more surface area now. So at this point, now your delta P's are going to start to be smaller, and there's going to be a break in that curve. And this pressure over here is going to be what is called the formation parting pressure. Similar to what we had before for the leak off. Before having the fracture, you have radial fluid flow. Once you go after the formation parting pressure, now you have a fracture that is also injecting fluid through the fracture. So now the fluid, some of it is going around the wellbore if it's uncased, and a lot of it now is going through the fractures. So what is going to be the relationship between the formation parting pressure and the minimum principal stress? What do you think? Is the formation parting pressure going to be higher than the minimum principal stress or lower? So formation parting pressure with the pressure at which you cause a hydraulic fracture by injecting a fluid that you actually want to inject, right? Like CO2, like water. This is not really mud. It's not a completion fracturing fluid. This actually you actually want to in the formation to stay there.
Maybe lower?
This one?
Yeah. Lower than SH-min?
No, it's going to be higher. It's going to be higher because you need to create a hydraulic fracture. If it's creating a hydraulic fracture, it has to be higher. And also, in this case, it is propagating that fracture, and you're losing a lot of energy in viscous forces where the fluid's going from here to there, opening the fracture. All of that takes work, and because of that, you need this formation parting pressure is higher than S3. Yes?
If we have hydrocarbon in the formation, would we still have leak off?
Yes. You will just push the hydrocarbons. Probably there your permeability, and it's not going to be absolute permeability, but it's going to be a relative permeability. But you will still, you can push the fluids as long as your pressure in the wellbore is higher than the pressure in the formation. You're going to push those fluids.
But would that affect it, like, I guess, long term, or?
You mean it's going to damage
No,
the
like-
formation?
I'm just wondering, like, it might reduce, like, after we stop injecting.
Yeah.
Our pressure is gonna go down, so, like, if there might might be less leak off, is what I'm saying.
Maybe, but then you're getting into that's probably a multi-phase fluid flow, other than the mechanics. Okay, guys, we have 2 minutes, and I want to talk about something very important related to. So in this case, we do want to inject a lot of fluid, but we do not want fractures. We do not want fractures because many times this stability test is done by regulatory agencies that deal with water disposal or with cases in which you want to regulate injectors so that you avoid fracturing. This is the objective, is to know what is that pressure so that later you do not go above that pressure, injection pressure. Why you do not want that? Because sometimes you may not want hydraulic fractures, right? An important case will be, for example, if you're doing water flooding. Let's say that we're doing water flooding, and here we have an injector, we have a producer, and we're looking from the top. This is SH min, and this is SH max. What happens if you cause a hydraulic fracture in this place? And let's say this is normal faulting. So SV is the highest. Think a little bit about that, and I'm going to put here the second case. This is an injector, this is a producer, but now this is SH min, and this one is SH max. What's going to happen if you fracture the injector in the first case? Let me tell you the answer. We're running out of time. If you fracture the injector in this case, your fracture is going to propagate like that, and you're going to bypass all the fluids that you were supposed to inject and sweep to get to the producer. Now you have a huge fracture that just the water moves from the injector to producer. So this is definitely not good, because you're fracturing the injector, it breaks through very quickly through the producer. In this case now, notice the orientation of the stresses. If you fracture the injector, actually that's not too bad, because according to the minimum principal stress in this case, now you will start sweeping from a larger front than what you did before, and that might help to the producer to get more oil. And you could also fracture the producer to extend the area in which you can recover the oil. So sometimes can be good, sometimes can be bad. It's very important to know what is the orientation of the principal stresses. All right, guys, I'll see you on Thursday. I'm